Okay, so thank you for the invitation. So very briefly, so I'm Gaël Chauvin. So I'm working currently at the Lagrange Laboratory in France, in the Côte d'Azur Observatory. And my background is really related to high contrast imaging and spectroscopy of exoplanets. So of course, that's why my presentation is really connected to that. So for this presentation, what I would like to do is, oh, check, it's not moving. Okay. What I would like to do is first to give you a kind of very broad picture of us in some sense, I think, which is, I think, a nice introduction to the topic. Then I will switch to a bit of a kind of a state of the art of where we are now in terms of direct imaging. And then at the end, I will go through, the big revolution, which is just coming with the extremely large telescopes. And of course, here, everything is targeted towards, the understanding of planetary formations and, for instance, the search for biosignatures and life and so on. Okay. So here to start, what I really like often is to show this this picture, which is a kind of mise en abîme, as we say in French. So it's one picture that was taken something like 5 years ago by the Cassini mission. So we're just doing a flyby of Saturn and just observing the moons of Saturn. And at one point, it just turned its way back, just behind and to that picture. And so you see, of course, a lot of darkness, and then there is one blue dot. So it's us. And so what is, I think, kind of very interesting, and just show how small we are and how fragile we are. I mean, the solar system, for the universe is a pretty crowded environment, but still, I think it's we are very small, in the solar system and in the universe. So trying to understand our origins and how life, just happened, on Earth is I think a very strong motivation, of course. Okay, so now if we take a step back in time, what we know, from just the beginning of everything, from the universe. So we have this picture, like the universe was, created like 13.7 billion years ago, with the Big Bang. So we had, the matter that just got into these large structures in the universe. We got the galaxies, formations of the first stars. And what we know is that about like 4.5 billion years ago, our sun, was born. Now, if we take, a very small piece of the sky, it's what Hubble did like something like 30 years ago, and you take an image, you have all these like multiple, spots that you find in the stars, in the sky, and they are not stars, they are galaxies. So by, observing very deep into the sky, what we see is that our sun is part of one galaxy, which is part of billions of galaxies in the universe. So we are really small. Now we know that our sun is really part of one, big structure, which is the Milky Way, our galaxy, typically located at a 2/3, in radius here. And we know that this galaxy, Milky Way, is composed of billions of stars. So in a way, our sun is, one star among billions and billions of stars in the universe. Now, if we talk about stars, as you know, maybe, I mean, the star is really defined by its ability to actually sustain the reactions, the nuclear reactions of fusion of the hydrogen, which is, of course, the most abundant element in the universe. And if we just take the sun and we look at, the populations of stars in the galaxy, what we see is it's not a star which is too big, like what we have here on the right, the O stars, extremely massive, but going to really burn very rapidly their hydrogen and then explode into supernova, and then, enrich the environment, with nucleosynthesis with heavy elements. No, we are like much, at a smaller scale, but not so small like the M dwarfs, which are typically something like twice smaller or 10 times smaller, in mass, and which are actually the most abundant stars in the galaxy and in the universe. Okay, So we are just, in between. This said, what we know also from, the observations of stellar formation, star forming regions, is that our sun, formed pretty rapidly, something like, 100,000 years, in this like huge, structures that we can, observe, in our galaxies that are like what we call star forming regions or stellar nurseries. And they are like, clouds of gas and dust. And what we think is like, you can have like very close to this like environment, you can have like a very massive star that is going to explode. You will have like a kind of shock wave that will propagate through the clouds and then provoke a kind of turbulence that will fragment the cloud. And by gravitation, then you will have the formations of the small stars. A nice way is that a nice illustration is actually this simulation. So here I have a typical size of a molecular cloud that is observed, in the star forming regions. And you see through the turbulence, then you have these fragmentations of the clouds. You see a lot of filaments that are actually present. I mean, the color code is actually related simply to the density, of material that you have. And then only by gravity, simple force of gravity, you're going to have the contraction, of the material. And then you're going to start to form these like baby stars that directly are going to interact dynamically between them. So you will see, we are zooming inside the cloud, and then you will see the white dots. So the small stars that are forming and directly interacting together. All the material also is interacting with the stars. You will see some stars that are actually flying with some edge on disk, some stars that are actually completely ejected, some that are will remain binaries. So you have some multiplicity with the stars. So already with that scene, which is like pure simulation, but based on what we have from the observation, you see that you will be able just through gravity and with just this like turbulence that is coming from outside, just to have a large variety of outputs. To explain the multiplicity, we know that when you observe a star, many of them are multiple depending on the stellar mass. And you see also that many of the stars after the stellar formation will have some material. And you see that the stars, they have some motion. And then this motion, so the material which is spherical at the beginning, like a kind of envelope, with the rotation is going to take the form of a disk. And this is the next phase, which is a phase of planetary formation, which is typically happening between 1 to 10 million years. So here, your star is formed, so still contracting, and probably quite soon will start the fusion of the hydrogen in the core. And then in the surrounding, so you have this huge disk of what we call a planet-forming disk, gas and dust. And inside this disk, then you will have the formation of the planet. So first we think that we will form the giant planets. And the key mechanism, which is we don't have like a one universal mechanism which is able to explain everything. Currently, we have one mechanism, which we call a bottom-up mechanism, which is going to form the core of the giant planets, with very small planetesimals that are going to collide. And then just increase in size. The core is going to increase in size to a typical size of 15 Earth's mass. And this will provoke a kind of runaway accretion, so interaction of this core with the environment. So the accretion of gas that will form the atmosphere of the giant planet. So this is the current vision that we have. And when we look at young stars, we see also that the disk is dissipating quite rapidly. And after 10 million years, I mean, you have less and less material in those disks. So that's why we have also a kind of like time constraints for these formations of planets. Okay, here you have like a kind of illustration of this process. So here you have the core of the star, which is like a kind of envelope, coming from this like remaining material from the molecular cloud. Then you have the formation of the star in the middle, and then in this protoplanetary disk, the small bodies are going to form the core. So you see, actually, I think it's probably Jupiter that you have just here, forming the core, and then you have the atmosphere that is formed just around, and then in the central parts, then you will have the formations of the smaller planets, the telluric planets, that will just happen after that, and that are completely dependent of what is happening with the giant planets. If the giant planets are moving, they're going to disturb everything. And we know, for instance, that for our own system, when Jupiter moved with Saturn, it was like created a big mess, and including what we call the heavy bombardments. Okay, now if we look at this picture, we can call it home. And in a way, we have a very peculiar architecture. It's our solar system. So we see the Kuiper belt, which is located at 50 astronomical units. So the astronomical unit for us is like the distance between the sun and Earth, and it's used for all measurements, planetary system. So we have the Kuiper belts at 50 astronomical units, and then we have the 4 giant planets. And then at about 3 astronomical units, we have an inner belt, which is the asteroid belt. And then inside, we have the 4 telluric planets. Okay. And so a big question for us is to understand if this typical architecture is something important at the end for the emergence of life. I will come back to that. Okay, from our solar system also, we see these 2 families of planets, the giant planets, and then the telluric planets. Of course, the giant ones, mainly composed of hydrogen and helium, and the telluric ones where they have more complexity actually, in the composition of those planets. And then what we have on the right are, of course, the exoplanets. The new family that came in line something like 30 years ago, and they are defined as planets around other stars than the sun. And then you will see there is a huge zoo, huge diversity from 30 years of observation. So this is summarized in this typical diagram where you see the planet mass in Jupiter masses as a function of the semi-major axis. So remember, 1 astronomical unit is actually, the distance, from of Earth from the sun. Okay, and this is actually all the exoplanets that have been discovered so far. And you see that classified by various techniques. So the transit technique here in yellow, where you just see, a periodic drop of flux created, by the planets passing just in front of the star. Then you have the radial velocity in green, which is kind of, Doppler shift effect of the planets on the central star that you can measure. You just, measure in a way the periodic variation of the velocity of the star. Then you have in purple, you have the direct imaging. So where there is just like a picture, it's kind of very intuitive. And then you have also the microlensing, which is just here in blue, where you have a kind of, deformation of the light of the background source created by a kind of lens, which is multiple. And then you can have an information on this like secondary body, which is a planet. Okay. So this is a typical picture that we have. Okay, a huge diversity. So you see the solar system. You see we have systems that are completely, different from our own solar system. What you see also is that this diagram is not homogeneously, sampled. You see that we have a lot of concentration here and there. Why? Because we are completely limited by the instruments that we are using. That's the first thing. Second point, as I was saying, if we were trying to observe, our solar system from very far away with our current instrumentation, we would barely see Jupiter, nothing else. Okay, so something that is actually missing is really to explore everything and to see if our solar system is, in some sense, is something which is common, in this zoo of exoplanets. The fact that we detect a lot of planets, I think, it really shows that the planetary formation process is something very efficient. Now, the formations of systems similar to our solar system, it's another question, okay? And I think it's really important also to understand if, the formations of our solar system and its specific architecture that I was mentioning is actually possibly related to the emergence of life. Okay. So where do we stand today? So about like 5,000 exoplanets, and from these 5,000 exoplanets, about 100 systems have been actually imaged with the specific technique of direct imaging. So here, what I will do, I've been 5 years in Chile, so I will be really focused on some observatories in Chile. I would just try to illustrate some, breakthrough discoveries that have been obtained, in the past years with two big observatories. So the first one is ALMA on the north of Chile, so observing, in submillimetric wavelengths. And the second one is the VLT at Paranal, which is optical infrared, multiple telescopes. Okay, ALMA. So ALMA is one of the most advanced radio telescope. So it's located at 5,000 meters of altitude in the north of Chile, and you have 64 antennas that will actually recombine the flux at the submillimetric wavelengths, and this will allow you to observe what we call the cold universe. So it's particularly interesting for us, for people trying to understand the initial conditions of planetary formation. Why? Because you can really try to understand and to characterize the gas around this, like in this huge disk, planet forming disk, but also the dust that is also present, or composition, and try to really understand what are actually the initial bricks of the planetary formation. So in 2018, there was a very nice result that has been published by the D-Sharp team. And what they have been doing is just observing young stars, so kind of, baby suns in the star-forming regions. And they obtained this kind of images with ALMA, with the very high spatial resolutions of ALMA. And what you see is like, portraits of young solar systems in formations. I'm not observing, it's not galaxies, they are like young stars. And you see a lot of, variety in the substructures that are present in the planet-forming disk around the stars. You see spirals, you see rings, and gaps. You see what we call vortices, so concentration of dust, in a given location. And so it's just showing you that, planet formation is diverse. And here you can already think it can maybe explain, the diversity I was pointing in my diagram. Okay. So then when you switch, you focus on one system. So here it's one system, 8163-296, where you see these rings and the gaps. Directly, what you can think is what is causing this specific structure? What is the physical process behind that? And what we think, it's actually the formations of giant planets. The planets are forming, and they are going to interact with the disk and create those gaps inside the disk. Okay, so it was a very nice, I would say, confirmation of what we had, in mind for the formations of the giant planets and the interaction with the planet-forming disk. Should I answer to the question now, or?
Whatever you prefer.
Up to you.
Maybe just because it's a methodology question, it makes sense to clarify it now, perhaps.
So what's the question?
The question was, what do we mean by interferometric? So maybe explaining interferometry?
Wow, that's a big question, because you could do a seminar on that. So in a way, instead of having a huge telescope of 300 meters, what you can do is you can use smaller telescopes that you will recombine them, and you will have a kind of huge telescope of 300 meters, but for some given spatial frequencies. So it's what we're doing. So it's a way of having access to a much bigger spatial resolution than what we could with a smaller telescope. I hope I answered the question. Okay, let's continue. So then, coming back to this system. So there. Okay, so of course you can take images, as I was showing you PANMA, where you can observe the cold dust, but you can also access the chemical composition and the chemistry. And what was found is that actually, on those disks, you have, of course, you have hydrogen. You have also more sophisticated, molecules, but you have also molecules that are much more complex than when we had in mind. And we found some amino acids, which are the typical bricks for the formation of life. So it's super interesting. So we see that, the nature is much more diverse than what we had in mind. Okay. So then, coming back to this system. So here it's one system, 8163-296, where you see this ring and the gaps. Directly, what you can think is what is causing this specific structure? What is the physical process behind that? And what we think, the nature is much more diverse than what we had in mind. So it's super interesting. So we see that, the nature is much more diverse than what we had in mind. Okay. Connection to that, at about the same time, 2018. So in parallel, there was like another kind of instrument, Planetary imager, so high contrast imager, that was put online actually in 2014, and really, observing also this young system, but this time not in the submillimetric wavelengths, but in near infrared. So these kind of instruments are kind of complex. So what they are doing is they are combining various steps of technology to try to improve the angular resolution of the telescope and the contrast. So that's what I will try to describe now. So here, for instance, that's a typical image of a star that you will observe with a very large telescope from the ground. It's like blurred. And what you have, the problem is the turbulence of the atmosphere, which is just above the telescope, is actually degrading completely the quality of the image. What you need to do, you need to plug what we call an adaptive optic system that will correct for the distortion of the turbulence and then restore what we call the diffraction limit of the telescope. So any optical instruments should access a spatial resolution, which is lambda over d, so the wavelengths over the diameter of the telescope. When you plug this adaptive optic system, which is a real-time system working at something like about 1 kilohertz, you can restore actually the quality, so the spatial resolution of the telescope. And then what you can see is, so this is in near infrared, you can access also to higher contrast. So the contrast is a typical ratio between the faintest source you can detect in the noise and the maximum of the flux of the PSF. Okay. When this is done, what you can do as a second step, you can use chronography. So chronography was invented something like 1 century ago by Bernard Liot in the south of France, just to observe the sun. It was just blocking the light of the sun, just to observe the environment of the sun. It was actually taking video, and people were thinking it was crazy. And when you do that, okay, you block the light of the star, and you can start to improve actually the contrast by 1 order of magnitude. So you can detect objects that are much fainter compared to what you were doing before with that chronography. And then the third step is to use what we call differential imaging techniques. So I could come back to that in the question, where you can actually remove the remaining speckles. So the small dots that you still have that are related either to the instruments or the fact that the correction of the adaptive optics is not perfect. And so you can take some kind of temporal references or spectral references or polarimetry references that can help you to reduce the signal of the star, but still conserve the signal of the planet. And you can get at the end these kind of images. So the contrast is then improved by 2 orders of magnitude, so 10 to the 6. And then you can see planets, you can see disks. So this is one very famous example, but that's a bit the philosophy. So you have these various steps then to access the ground of detecting the planets directly in imaging. Okay. So now Sphere has been doing a lot also of observations of young systems. This is just a kind of gallery. So not the same system that were observed with ALMA, around stars a bit more massive, but still showing the same diversity. Spirals, shadows, in your disk. Here you have some filaments, broad cavities, and something. Here you see gaps that are present. So again, confirming the fact that we are seeing structures that are similar to what is seen with ALMA. Here we are actually witnessing the light which is scattered by smaller grains, and more on the surface of the disk, but still we are seeing this kind of structures. And so what happened is at one point we had, of course, the synergy of the 2 observatories, ALMA and Sphere, on one specific system. And this huge discovery was PDS-70. So this is a nice ALMA discovery in image that was published this year. So here you see it's a really kind of baby solar system. You see an outer belt, which is a kind of 3D crypto belt, analog to our crypto belt. There is an inner belt, which is not well resolved here. So it would be a kind of analog to our asteroid belt. And then a broad cavity. I will come back to this point after. Now you take this system and you observe it with Sphere. And this is what you see. So you see the disk, the outer belt. And then in the cavity, you have a bright blob, and this is a planet in formation. So now we have the proof that what we're seeing, these cavities, these rings, then we have clearly here a planet which is inside, emitting light, and then responsible of carving the disk. This was a really nice discovery in 2018. Then we have some information, of course, on the orbital parameters. We got some follow-up observation, and here actually you have a hidden planet, so there's a second planet in the system. And then what you can do, you have the photons of the planet, so you can disperse the light, and you can get some information on the spectrum of the planet. So it's what we did. Oops, I lost the spectrum, but so you have to believe me. So you can get actually information on the composition of the molecules that you have in the atmosphere, water, carbon monoxide. And so you can really start to try to characterize actually the physical properties of this protoplanets in formation. What was also particularly interesting is, as I was saying, so you have to believe me, there is a sea planet, which is here hidden in that signal. And if I come back to the ALMA image, it's actually corresponding to this signal. And what you see here is not the signal of the planet C, is the signal of the disk around the planet C, the reservoir of material around the sea planets, which we call a circumplanetary disk, which is actually the reservoir where you're going to form exomoons, for instance. So this was also a very nice confirmation that you had around this planet C, which is real, material, which is just in the form of a disk, as expected from the theory of formation. Okay, of course, this is not the only system which we can see as a really close analog to our solar system. We had other systems a bit more evolved. This one, HR8799, that was already discovered about like 13 years ago, 14 years ago. Here you see also the nice ALMA image, which is actually quite faint, but you see the Kuiper belts of this system. And in the inner part, you have 4 giant planets that have been observed in direct imaging. Here you have the accumulation of the various epochs. So it has been obtained, I think, in Keck, at Keck, in Hawaii. And you see the 4 planets that are moving. Here, what we know, again, so we have a kind of Kuiper belt analog, which is, outside. And then you have an inner belt that has been also, detected through the spectral energy distribution of the star in the internal part, a kind of, analog to the asteroid belt. So you have something very similar. And so it's where we are now. And when you see that, you say, oh, I'd like to go in the center. If I have giant planet there, if you have a Kuiper belt analog, an asteroid belt, I must have some kind of telluric planets in the middle. So here, that's pretty much a challenge of the extremely large telescope, to access this really close region, what we call the planetary forming region, where you expect to have the bulk of the formations of giant and telluric planets, and you want to access this window to start, characterizing all the properties of the smaller planets and possibly, accessing, the signature of life. Okay, so where do we stand now regarding what we have next? So the extremely large telescope. So the first thing you can see is, so it's a kind of very complex diagram where I put a timeline and all the projects related to exoplanets from the ground or from space. What you see, many projects connected, of course, to exoplanets, which is a very hot topic in modern astronomy. From the space, of course, you would see GWST, just now almost ready, to observe. Plateau, NGRST, and in the long term, ABEX, LUVOIR, and LIFE. And from the ground, a lot of instruments that are still working, of course, on 10-meter class telescopes. But then the big step is 2027. So where we have the first extremely large telescope that will come online. And for us, it's going to be really a game changer, as I was saying. Why? Because they're really going to open like a new horizons in terms, of capability. So of course, bigger telescope, you will have an increased sensitivity. So you will be able to detect fainter objects, fainter planets. Bigger diameter. So if you have an adaptive optics system from the ground, then you can access the diffraction limit of the telescope. And so here, it's a factor of like something like 5 compared to what we have now, the ELT. So you can go down to a scale of 10 milliarcseconds. So it's a really small angle. So for a typical young star at 50 parsecs, it's like 0.5 AU. So within the orbit of the Earth. So you see that you have already the overlap of what you can expect with the architecture of the telluric planets. And something also which is very important and synergetic with space is that you have, the telescopes are going to be there for 30 years. So you will have various generations of instruments, and you will learn from the first generation to build the second generation and the third generation. So you will really continuously push actually the technology and the science with those telescopes. So here I will take the specific example of the ELT, the European Extremely Large Telescope, because I've been involved, into the preparation, scientific preparation, also various, instruments consortia. So here the roadmap is pretty well advanced, and the technology of the telescope remains very challenging, particularly challenging for the European community. Why? We have probably this is the biggest, telescope of its class, like a 39-meter. Also, the primary mirror is going to be composed of 800 small segments that are going to be phased. It has never been done before at ESO. There is a big experience, in Hawaii with the keck. That's really a first for the ESO community. Then, if you remember, I was talking about adaptive optics. So far, all the adaptive optics systems were built apart from the telescope within the instruments. Here, for the first time, we're going to integrate directly the adaptive optics system inside the telescope, which is also a big challenge. And one of the deformable mirror, which is M4, is going to be composed of, of course, you have the mirror, which is like kind of flexible, and just under you will have something like 3,000 actuators that are going to compensate the effect of the turbulence. And here again, that's something which is kind of new. It's going to be a kind of a bit scary at the beginning. Regarding the roadmap, as I was saying, it's pretty clear. We have a first generation of instruments that are going to come online in 2027. Very generalist instruments. So the goal is, of course, to serve a maximum of people, in the scientific community, from cosmology, extragalactic, galactic, stellar population, and exoplanets. And we're going to have then a second generation of instruments, then second and third generation of instruments that are going then to be much more focused in terms of science. And if we think about PCS, it's going to be a planet imager completely focused and targeting, the detection of telluric planets, ideally under characterization. Okay, now briefly, of course, to show you the key science drivers. So first one, of course, is to go back to these planetary formation zones. Here it's a kind of, very simplistic diagram of this planet forming disk that I was showing, for instance, with Palma or with Sphere. And so far, we are actually, cutting, the information just here at about, I'll say 10 astronomical units. So we can observe what you have outside, but we don't have the spatial resolution to observe what you have inside, and where you expect to have, as I was saying, really the bulk of the planet, the populations of giant planets and telluric planets. So here, all the point will be to observe that and characterize the properties of the disk and the initial conditions of planetary formation. That's really something which is super important. Second aspect, we will gain in sensitivity, and it will allow you to do much more advanced characterizations, for instance, of the giant planets. So we will improve the contrast, and then we will be able to use, because we have more sensitivity, more spectral diversity, and then to start doing some crazy things like what we call Doppler imaging. So you can really map, actually, for instance, all the atmospheric circulation of the giant planets. So this is one example, which is actually one observation of a brown dwarf, Luhmann 16, which is actually one of the closest brown dwarfs that has been observed so far. And so we will be able to do the kind of same thing for the giant planet. Of course, with the second and third generation of instruments, the big challenge will be to access even closer separation. We hope to get to 20 milliarcseconds and higher contrast. This is particularly important. Why? Because we're going to change the paradigm. from observing planets in emitted light, in direct imaging, to observe planets in reflected light. If you go closer, then you can be much more sensitive to the reflected light. And this is going to be a game changer to observe telluric planets, because there you're going to observe the reflected light of the telluric planets, and you're going to target really nearby stars, stars really close to us, just to maximize this detection. Okay. Then, as I was saying at the beginning, currently we have a very imperfect view, in this kind of diagram, where you have the mass as a function of the distance from the star, as I was saying. We see the various categories, families of planets that are observed. So the hot Jupiters, temperate Jupiters, cold Jupiters, and then the hot Neptunes and super Earths, with like transit observations. There will be also key observation for James Webb. Okay. And so now, or in the coming years, that's what we're going to do. We're going to push with James Webb, a pretty broad separation in direct imaging, because we have a limited, a primary mirror. We're going to be much more sensitive in space. So maybe go to exosaturns at more like 30, 40 astronomical units. Gaia is going to give us also some more information just in the middle. And then we have all the transit information, and also from James Webb, get much more information on the atmospheric properties of very small planets, really close in. Okay. The ELT is going just to be bridging the two inner part and external part. And so to give us a much more complete, information on the demographics of giant planets and the smaller one, the telluric planets. And something particularly important and interesting for us, what we call the temperate rocky planets. So where you might expect to have liquid water, for instance. So this is going to be, of course, one of the biggest, challenge of the ELT, to have the instrumentation, like I was saying, PCS, for instance, this third generation instrument, to access this region, what we call the habitable zone, and then to be able to image and characterize the planets that are present there, and possibly actually to detect the first, informations of biosignatures that can be present. We have to be careful, because it's not a simple thing. It's just not a simple tag, that you find. We need much more information to be sure that we have a planet which is possibly, habitable, might have life. Okay. Okay. So to conclude, so what next? So slowly but surely we are going toward the understanding of our cosmic origins. I mean, you have to think that 30 years ago we knew nothing about exoplanets, and we stand now here, 5,000 exoplanets detected. We have, ExoMars. We have probably, reservoir of exomoons. So there's a huge progress in this field. What we can think is that with the first light of the ELT, we'll have much more information on the giant planets, the formations, the demographics, the physics. But we will have to wait for the second or third generation of instruments on the ELT in the next 20 years to access the smaller populations of the telluric worlds, so the telluric planets, and start, having the possibility to search for biosignatures and so on. And this would be done also in synergy with space. Space and ground are very synergetic approach. And if it's not done from the ELT, as I was mentioning, there are possibly for 2040, 2050, even more challenging prospects with like LabX, UVOR, Life, that are trying maybe to be much more sensitive from space for this detection of biosignatures. Okay. So if you have questions, that's a good time.
Thank you so much for the talk here, Dr. Chauvin. That was super interesting, super informative. And we actually have lots of questions here in the chat. So okay. I don't know if you want to pick your favorite one to start off with.
To open my eyes. No, it's late here.
Would you like me to read one of them maybe?
Yeah, maybe.
Sure. Let's start with the first one here then that was asked. So someone's asking here, what are some of the largest factors of noise or uncertainties we need to reduce when observing exoplanets?
Okay, so I will answer for direct imaging because you can have an answer for each technique. For direct imaging, I mean, I can just, come back to my slide. Yeah, I had a nice picture, of the ELT in construction. If you go, and I think what I will say is really, it's really what you have on those slides. First thing, when you go from that step to this one, as I was saying, you need adaptive optics. Adaptive optics, it's working well, but it's not perfect. What we have is what we call this trail ratio, which is a kind of parameter to measure the factor of correction. 100% is a perfect correction. 90% is almost perfect, but is not completely perfect. And there is a big difference between almost and perfect, which means that at the end, you still have some residuals from the atmosphere that we call speckles that are actually correlated with the turbulence time. So they are moving, in time during your observation, and they can at some point mimic, a pure detection of an exoplanet. So this is one important source of noise that we need to reduce. How do you do that? So you need more advanced adaptive optic system. So going faster, for instance, and this is exactly what we're pushing at now. So trying to be capable just to correct something that has not already changed, So by going faster, then you can do that. So for instance, for Sphere, we're pushing a project which is called Sphere Plus to go to something like to 3 kilohertz. So to be much more efficient in terms of corrections of those speckles. Okay. So one limitation are these speckles coming from the atmosphere. The second limitation is coming from the instrument itself. So the instrument and the telescope is not, a perfect stable instrument. You have variation of temperature, the telescope is moving, so you can have some aberration that is coming from the telescope itself, and that actually also are called quasi-static speckles that are changing. So you need to have defined strategy to be capable of correcting that. And then even worse than that is you have the adaptive optic system, but the adaptive optic system is not correcting, the light up to the detector. It's correcting the light, and then you have the chronograph, and then you have the detector. So everything which is happening behind the adaptive optic system is not corrected. So you need to find also a strategy to correct this aberration, what we call the non-common path aberration, which are also a key limitation, for this contrast. And when you talk about reaching a contrast of 10⁻⁹ at 20 milliarcsecond, you're exactly in this ground of limitation. So you have to be able to correct everything, atmosphere, instrument, and then you'll be able to get probably actually the contrast you need for detecting the telluric planet. So I guess I answered that question.
Yeah, I think so. There's actually kind of one here that's a follow-up, kind of related to noise, I guess. And it's saying, how concerning are the current and upcoming deployment of constellations of internet satellites? So I guess those like mega constellation structures. How important are those to the astronomical community in regards to interference with imaging? Is that an issue?
Yeah, it's. It's so for us. Talking about the community of astronomers, of course, it's a big issue, and particularly because there is no control at all, actually. So that's a huge issue. In our case, I think because we are observing very small field of view, it's a bit less problematic. So compared to people that are doing, for instance, like wide field imaging, large field imaging, and so on for, I don't know, measurement of stellar population, galactic population, then yeah, it's a real problem, because it clearly is going to affect the quality of the observations and so on. In our case, yeah, it's a bit less of a problem because we are because we have a field of view which is so small, the probability is, of course, smaller. So, but yeah, we have some solidarity. So we are, of course, I think it's a huge issue for the astronomic world, and especially because there is no control currently.
Right. On a bit of a different note here, you mentioned a lot of future observatories and instruments that will be built in the coming years, but someone else is asking, do you think we will keep building larger and larger telescopes, or would we find new technologies to get more observational capability from what we already have? So is there a need to go farther, or can you develop adaptive optics to be better, to use what we have, or what is your thoughts there?
Yeah, it's a very good question. One thing that you see is already, even with the old instruments, for instance, something I didn't speak, about that, but for instance, like the data processing. Data processing is something also very important. And for instance, now by developing new tools, we are revisiting all observations. And that's why it's also very important that, everything is in open access, that all telescopes, can have archives that are available for everyone. Because with these new tools, by revisiting the old observations, yeah, we can really push, by having smarter, way to calibrate the observations, the problems of the speckles I was mentioning, or aberrations, we can definitively improve actually the performances of the observations. So this tool is something which is super important. Pushing the size of the telescope, yeah, I don't know. The ELT initially was supposed to be a 100-meter telescope. Okay, I would say that for our science case, yeah, maybe going to 100 meter would be nice. Going beyond, I'm not completely sure, because we're already, accessing the physical scale we need, which is this region between 0.1 to 10 astronomical units around the stars, the young stars or the nearby stars that we want to observe. Okay, so after that, it will be more a question of sensitivity, maybe. So yeah, currently, I don't know. I would say I think we still need to learn a lot from the next generation, which is not online. So first, from the first, light instruments, we will have a lot of, I think, discoveries about the way the telescope is going to behave. And then, as I was saying, the telescope is going to be on site for 30 years, 40 years. We will have, new prospects in terms of instruments. We need to push the capabilities of the ELT. If I take the example of Sphere, Sphere is based on the first instrument, which was called NECO. So Sphere was online in 2014. NECO was online in 2001. And so I did my PhD on the NECO instruments. And so we were super proud, of the instruments. And then after like 10 years, we were seeing a lot of limitations, a lot of problems. So there was the adaptive optic system, I don't know, the detector, many things. And so, yeah, you want to push, but it takes time. So the typical time from the ground to develop an instrument is something like 10 to 15 years. So it takes time. You need really to think about what you want to do and to really have a really good reasons to push a new instrument. So you need to really do the exercise of the lessons learned, and yeah, from space, that's another story. If you want to develop, a space mission, it can take 30 years, 40 years. So it's another way. But again, I think we really have to see that as really two synergetic approach. People working, on space telescopes, on James Webb, learn a lot from, the ground-based observations. And I think exactly, the opposite is also true. So it's not, one against the other. I think it's the two together. And after that, the first one will, discover the first biosignature. Yeah, that would be nice. But that will be, I think, for us, a major discovery, for humanity.
Yeah, it's an interesting question about whether, you always need to build something new, or if you can kind of fix what you already have or make it better. Yeah. So yeah, that was an interesting question. Speaking of the ELT, though, there is another question here about that, saying, would the ELT be able to detect the Kuiper belt or Oort cloud objects around planetary systems? So maybe like what you were talking about closer to the beginning, how there was analogs to those?
Well, this is ALMA, but here you see the outer belt of PDS 70. It's a Kuiper belt. It's already, it's what we're already imaging. So the ELT, of course, will be able to do it, and more than that, we'll be able to see, some inhomogeneities in the structures. You can think, for instance, for this system here, this is a clear spiral that we see. This is real. This is not something from the data processing, and we have new images. And you can see sometimes, you can imagine to have some, multiple rings tracing some, motion resonances, for instance, with unseen planets, like, Neptune's planets that are really close to the rings. So yeah, the ELT definitively would do that, and much better than what we're doing now. But we are observing already some kind of exo-Kuiper belt. This has been done. That's what you have here on this slide, for instance.
So it's basically just a higher resolution or a more detailed photo you'd get with the ELT.
Yes. So here it's one case. With the ELT, we want hundreds of cases because,
True.
I think something which is really important is always, try to understand if what you're observing is like a kind of Frankenstein, or if it's really something which is, the baseline of, the formations of the young planetary system. This we don't really know. Currently, we really, I was speaking about 5,000 exoplanets, but we're only speaking about like, at maximum 100, system image, so we don't have this we're just starting to have the statistical information. And so with the ELT, clearly, here you will have much more information on the demographics. That's what I call the demographics, is the statistical information to constrain the properties of the disk, outer belt, inner belt, but also the properties of the planets themselves, their distribution, in mass, or distributions in orbital properties, in composition, atmospheric composition. Yeah, so I think a good way to see that is, I think in the coming decade, we're going to switch, we see that already with James Webb, from an era where we are just doing survey, many surveys observing many stars. We're going to switch to characterizations of known systems. It's like, you can think that maybe in 5 years, 10 years from now, we will have almost complete cartography of the planetary system, really close to the sun. But what we will do is we will try to observe them in their globality. All the, the population of the giant planets, the population of the telluric planets inside those systems, how they are, related. Do you need, as I was saying, a system with multiple belts, giant planet outside, inner planets, inside, and then maybe do you have like a biosignatures? Is it something which is, as I was saying, the prerequisite, to have the emergence of life? Yeah, that's all the question we have. And I think in 10 or 20 years from now, that's the thing we'll be, I hope, able to answer.
Right. So I guess that's kind of where you see the field of exoplanets going then, is kind of more on the characterization side.
So yeah, so James Webb, you see, it's now more and more, focused on the characterization, particularly of the atmospheres. ELT, that would be the same. And then I think also what you have to think is that there will be also an extra pressure because for the European community, now we have 4 telescopes, we have ELT, there will be all behind one telescope. So people working on cosmology, extragalactic solar system, and so on. So there will be much more pressure. And so, yeah, trying to push on some really specific system would be extremely interesting. And so we will switch, as I was saying, probably from an era of surveys to an era of more like, surveys for detection to an era of surveys for characterization. And you have to think, so there will be Plateau that will come online. That would be really a survey missions in transit. So Gaia is going to have a final release, I think it's in 2024. And there are, discussion of having a Gaia 2. And Gaia will also, provide a lot of planetary system detected with astrometry that you will be able to do in follow-up. And so you really have to think that, as I was saying, in this diagram, 10 years from now, there was like some kind of families of people working with the techniques on different fields. And now we are here. So we are having a clear overlap of the techniques. Radial velocity with transit, radial velocity with direct imaging, it's already starting. Gaia will do the same. And then with ELT, yeah, we will have a full synergy. The synergy is particularly interesting. Why? Because each technique is giving you access to various observables, various physical parameters. imaging, you have the luminosity, you have the atmosphere, the orbital, parameters. Radial velocity, yeah, you can have the mass, which is super interesting. For instance, for direct imaging, for young stars, we have a problem because we are always using mass-luminosity relation, which are theoretical and not calibrated. So having this like synergy between Gaia or radial velocity and imaging is critical to really understand the formation of these young giant planets and their luminosity. So yeah, we're already started, and it's going to extend, exponentially.
So as a follow-up question to that, say you do this characterization, you move into this new era. It might be a bit philosophical, but someone's saying, if we move into this era, what if we find these biosignatures? What if we find these signatures of life? What happens if that happens? I don't know if you can answer that, but
you have more chance to witness that than me. You're probably younger. And no, first thing we can say is, that's why I'm very cautious when you show this kind of diagram or figure. There won't be one signature where you say, yeah, there is life. We found life. So we would have like, detective, yeah, we have a planet which is in the habitable zone. Probably actually, the star is not, I don't know, has not a lot of activity, which would be something which is bad for the emergence of life. And then we see ozone, we see methane, we see water in the atmosphere of this planet. Then we have a pretty good probability that that's something which is favorable for life. Okay, so we will need, I think, various diagnostics just to be really sure. That's one thing. Something we have to keep in mind is that when you look here, the spectrum of the Earth, you say, yeah, that's easy. We have carbon dioxide, ozone, water, but for during like 3 billion years, the spectrum of the Earth was like Venus. Okay, so it's not because you're finding a spectrum like that life is not going to happen. So primitive Earth was not habitable at all, but then has evolved to what we have now, and it took time. So that's also thing that you have to keep in mind. It's also related to the evolution of the system that you're observing. Okay, so yeah, so it's not as simple as just one simple signature that you observe, and then the impact is going to be huge. Of course, then the thing is, people are going to say, okay, let's go there, and then no, here we're just observing, and the hope is really to detect that. The question of going there, it's for us, it's not science for the moment.
Right. Yeah. Yeah, it's a lot of it that's very sensationalized too. Like we found life here just because there was one element or whatever that you observed. So it's interesting to hear there's a lot of factors that go into that.
Yep.
We're almost out of time, but there is one last question in the chat here, if you have time to answer it. It's a question here more about just general differences in observing gas versus terrestrial planets, if you could offer some insights there.
So can you be a bit more specific by differences?
Maybe when you're observing the system. So are there certain considerations you'd have to take into account if you want to observe a gas giant planet compared to something that's like a super Earth?
So, what I can tell is if you want to observe in direct imaging super Earth, you really need to be in a regime where you will be able to observe the reflected light on the super Earth. If you're just expecting to detect the emitted light, forget it. It's not a contrast to 10⁻⁹, it's much more. So you need to think that you will be able to see really the light reflected, on the surface of the super Earth from the star up to you. Okay, so you have to design your observing strategy and your instrumentation for scale, which are, here, as I was showing on that plot. You have to be clearly under one to two astronomical units to be really have this sensitivity, which is going, to be much higher when you go closer. Okay. For giant planets, what we are observing now is that for very young systems, the young planets, they are hotter when they are young, and so they emit more light. And so that's why they are easier to detect. That's why we are detecting in imaging young planets and not old planets, because when they are old, the planet, they are not sustaining, the fusions of hydrogen. And so they are just, cooling in time and getting fainter and fainter. So all planets are much more difficult to observe. So yeah, here, if we want to observe, the demographics of giant planets, it's easier to start with the young planets. But with the sensitivity, the increase of sensitivity, I think we might start to have more information on the giant planets, and possibly also with the reflected light, even for giant planets which are closer in, and we know there are lots. Then we'll be also able to have a bit of information in this specific region. Okay. So I don't know if I completely answered the question, but yeah, you have to think that you will have clearly different strategy of observation and even possibly different design of instruments.
Interesting. Yeah. No, I think that was great. And I think with that, we're actually a couple minutes over time here, so we'll probably end it. But thank you so much, Dr. Chauvin, for coming and talking today. That was super interesting.
Good.
So no, it was really great. So we really appreciate it. And yeah, thank you so much.
You're welcome.
Okay, awesome. So just as a reminder to everyone else, our next talk will be at 8 p.m. We have Dr. David Reitze from LIGO talking to us. So the fun continues, the science continues all night. So thanks everyone. And thanks again, Dr. Chauvin.
Okay, bye.
See you.